In this video, we talk about modal frequencies simulation. Why would you use this tool, what the workflow and capabilities are, and what results it produces. All objects vibrate when acted on by an external stimulus. The vibrations occur at various natural frequencies and with varying shapes, each referred to as a vibration mode. Typically, you want to avoid exciting a structure at one of its natural frequencies, or the vibration will be amplified. This phenomenon is known as resonance, which can lead to fatigue failure. Conversely, in some applications you might want the object to resonate to maximize the produced vibration. An example is an ultrasonic cleaner or toothbrush. This model is a tuning fork like a technician uses to tune a piano. Here we see the fundamental vibration mode of 440 Hz, which is the standard A4 musical note. The length of the prongs has been fine-tuned in the Simplify workspace to achieve the target pitch. Now let's take a look at the process of setting up and solving the study. The first time you enter the simulation workspace, the new study dialog appears automatically. Choose the Modal Frequencies Analysis type. Then, click this button to access the study settings. We'll choose to calculate 12 vibration modes. Analysis guidelines dictate what percentage of the structure's mass must participate in the computed vibration modes. These guidelines affect the number of modes you have to solve to achieve the target mass participation. We'll look at mass participation factors a little later in this video. You can apply global and structural loads to modal frequency studies. Tensile or compressive stresses increase or decrease the natural frequencies respectively. An example is the way the musical pitch increases as you apply more tension to a piano or guitar string. Activate the Compute Preloaded Modes option to account for the effects of applied loads. The tuning fork is not preloaded, so we'll leave the option unchecked. We'll define an absolute mesh size of 1.2 mm, resulting in 4 elements through the thickness of the prongs. This size should faithfully capture the strain gradients and produce accurate modal results. Next, specify the study material. AISI 304 stainless steel has already been specified in the Modal workspace, and we'll keep this material for the simulation. The model can be constrained or unconstrained. A tuning fork is lightly held in the fingers of the user. A rigid constraint would likely distort or impair the vibration modes, so we'll leave the model unconstrained. We are ready to solve the study, which can be done locally or in the cloud for this analysis type. The displacement results are displayed as soon as the solution is finished, and the natural frequencies are listed for each mode in this drop-down selector. Since the model is fully unconstrained, we expect 6 rigid body vibration modes: X, Y, and Z translation and X, Y, and Z rotation. Animating the results provides good visualization of the modes. Note that the displacement results are normalized to 1 length unit maximum. The values aren't scaled to any particular excitation and are only meaningful for demonstrating the shape of the vibrating structure. You can't infer the stress level or the actual displacement magnitude, which depend on the excitation that drives the vibration. You can view the total displacement or the X, Y, and Z components of displacement. Mass participation factors are available from the Results drop-down menu. The factors are calculated separately for each of the 3 global directions and for each mode. The total cumulative factors are listed at the bottom of the table. Since this model is unconstrained, 100% participation is achieved by the translational rigid body modes alone. This behavior would not be the case for a partially or fully constrained structure. Thank you for watching.